So, I will prove the direction. So, I have to prove that one direction, right. So, if limit m tending to okay. So, this is one direction, other direction is I should say that if x n tends to x almost surely I have to prove this happens. So, first I will prove this direction, okay. Let a of epsilon equal to intersection m equal to 1 to infinity union n equals m to infinity a n epsilon. So, this is a familiar object, right. This is the event that, so this is what is this event. So, this is nothing but this is the event that a n infinitely occurs infinitely often, correct. This is an old foe, we have encountered this in Borel-Cantelli lemma proof, right. Okay, great. So, now I am going to say, so what have I assumed? I have assumed this limit is 0, is it not? You know what, I am actually trying, so sorry, I am actually what I am trying to prove is actually the converse, I am sorry. So, I am proving that if, sorry, so I started the wrong proof. So, if x n converges to x almost surely, then okay, I will prove this first, okay. So, if x n converges to x almost surely, then clearly probability of a epsilon equal to 0 for all epsilon greater than 0. Let us see if you agree with that, okay. So, I am assuming that x n converges to x almost surely, okay. So, but if x n converges to x almost surely, then I am saying that for any epsilon I must have only finitely many excursions. So, I must have only finitely many epsilon excursions, because you have convergence almost surely. So, at some point you should be always within that epsilon band, only then you say with probability 1 you have to be within that epsilon band, right. So, which means you have to have only finitely many excursions, because if this is not true then you will not have convergence with probability 1, correct. So, we have thus probability intersection m equals 1 through infinity. Now, you look at that, what is this guy? What is inside this box is b m epsilon, right, that is what I have defined it. Correct, you will agree with that, right. I have simply rewritten this bit. Now, I can do something, right. Now, I can, so I do have, so these b m epsilons are nested. Now, you have to tell me whether it is nested decreasing or they are nested decreasing, right. b m epsilons are nested decreasing, they are Russian dolls. You see why? Because Bm epsilon is the event that there exists some epsilon excursion m or beyond. Okay. So, if you have some excursion m plus 1 or beyond, you are guaranteed to have an excursion m and beyond. So, BMs are nested decreasing, they are Russian dolls, which means I can invoke continuity of probability measures. By continuity of probability measures, we have limit m tending to infinity, probability of, correct. So, one way I am done. Okay. So, I have proven this statement then, right. Now, I have to prove the converse. Okay. It is a little bit more tricky, yeah, I have to think about it differently, it is not necessarily more tricky. So, the converse I have to prove that if limit m tending to infinity then xn converges to x, almost sure. So, I mean if so, this is all for all epsilon greater than 0, right. Everywhere it is for all epsilon greater than 0. Now, see the key to this proof everywhere is that, see throughout, so it is actually, this is not just if then, it is actually equivalent. Okay, maybe I should, so this condition that I have said, right, xn converges to x almost surely is equivalent to saying that there are only finitely many excursions, correct, right, for any epsilon greater than 0, that is what I am going to use, right. So, more formally, let C be the event that xn of omega approaches x of omega. Okay, I want to prove that probability of C equal to 1 when this is satisfied, right. So, I can use, what I will prove is that probability of C complement is 0. So, let me just keep this figure. So, I am going to prove that probability of C complement is 0. So, so what does C complement mean? C complement means that xn does not converge to x, okay, which means that no matter how big an n you look at, there is some excursion, right. So, that is what we will use, okay, probability of, so I will write it like this. So, C complement is the event that there is no convergence does not happen, which means there must be some epsilon for which A of epsilon occurs. Now, what is A of epsilon? There are infinitely many excursions, right. So, if convergence does not happen, see convergence is the same as saying beyond some n you are within that epsilon band for any epsilon, correct. If you do not have convergence, then for some epsilon you have infinitely many excursions, correct. So, which means there exists some epsilon for which, so you can write it like this. So, C complement is the same as saying there exists epsilon for which there are infinitely many epsilon excursions. Agreed? So, A of epsilon is the event that there are infinitely many epsilon excursions. So, now, so there exists some epsilon greater than 0 for which there are infinitely many epsilon excursions. Okay. So, now this is a little bit of a problem. So, we have never encountered a situation where you have a uncountable union, this is an uncountable union, right. So, what you do is you convert it into a countable union. So, this is a standard trick in measure theory, probability theory and so on. So, you say union over m equals 1 through infinity A of 1 over m. You see why these two are the same, because if for some epsilon which is not of the form 1 over m, let us say there is an excursion for, so let us say this occurs for some epsilon greater than 0, that epsilon need not be of the form 1 over n, but you can always find a large enough n for which 1 over n is smaller than that epsilon, correct. So, if you have infinitely many excursions for epsilon equal to 0.0028 or something, you can always find an integer, let us say m, such that 1 over m is less than 0.0028. In particular, I can take m equal to 1 over 0.002, right, something like that. So, you can always do that. Going from an uncountable union to a countable union is not a problem. Fine, right. So, let us say epsilon is, suppose you have an excursion, suppose you know that A epsilon, there are infinitely many excursions for epsilon equal to, you give me a number, huh. So, let us say it is like 1 over some big number, right, let us say it occurs for 1 over 10,000 pi, just for the sake of it, okay. For epsilon equal to 1 over 10,000 pi, you know you have a excursion, right. So, you can always take, so how is this, this is like 3000 something, right. So, you take m equals 4000 now, right. So, you have infinitely many excursions for that epsilon. So, you will definitely have infinitely many excursions for epsilon equal to 1 over 4000, correct. So, there is no loss of generality in doing that, right. This is something I want you to appreciate. So, now it is easy, right, now you know how to deal with this stuff, right. So, this I can use union bound, correct. Okay. So, I have to prove that probability of, so if, so I have the summation of the probability that there are, so there are all these terms, right. I want to prove that each of these terms is 0, probability of each of these terms I want to prove is 0, okay. How does that follow? It follows from, so it follows from here, right. I have assumed that, so probability of A epsilon is equal to limit m tending to infinity of this guy, right. So, I want to show each term here is 0, okay. As long as this is equal to 0. So, I think I am using the same m that is causing a little bit of confusion, let me see it, okay. So, I may maybe I should put a k here instead of m. Okay. Let us see. Now, I want to look at probability of A of, consider probability A of 1 over k. Okay. This is equal to the probability that intersection m equals 1 through infinity. So, yeah, throughout you just write k, okay, just so that we do not mix up with our bm them there, okay, just write k here, let us just write k, okay, all this is k, this is also k, okay. This is equal to you agreed. See, probability of A of epsilon is nothing but the probability that it's the probability of A of 1 over k is the probability that there are infinitely many 1 over k excursions, which I am writing like that, agreed. So, this is equal to, by continuous probability, this will be equal to limit m tending to infinity probability of bm of 1 over k, okay, and this is equal to what? Why is this 0? Because that is what I assumed, correct. So, this is equal to 0 by assumption, correct. Thus, probability of A of 1 over k is 0 for all k greater than or equal to 1, correct. So, this summation will be equal to 0. So, if you are summing an infinite number of zeros, you get a 0, okay, let there be no confusion about it, right. Sum k equal to 1 to infinity, 0 is 0, right, there is no confusion about that, right, which means probability of C complement is 0, therefore, probability of C is 1, okay. So, is that clear? So, go over this theorem properly, okay. This proof of this theorem really brings out the qualitative nature of this almost shear convergence, okay. So, what this theorem is saying is almost shear convergence is equivalent to saying that there exists some m beyond which there are no more epsilon excursions for any epsilon greater than 0. All your epsilon excursions end at some point, and after that your sequence is constrained to lying within that epsilon band, okay.
Why can't we go back as in the first code? As if limit the intention from the medium of epsilon is 0, we can use continuity inverse.
I have used continuity of probability, right.
Initially, first one also we can use continuity of probability and go back as in the first code. As we write in the first code.
So, you are saying that you can just retrace your initial proof. So, the only step involved there is that you have to go from here to here, that is exactly what I have done actually, right. So, you have to go from an epsilon to some countable index, that you have to reason. After that, that is exactly what I have done, okay. Then this union bound also helps, okay. Okay, so therein lies the qualitative difference between convergence in probability and convergence almost surely, Okay. Convergence is just convergence in probability just says that n of epsilon probability goes to 0. So, convergence in probability always looks at just one n, forgets about the rest of the sequence, okay, only will look at a particular n, okay, and sees what is the probability of an excursion. Okay, look at fix an n, look at the probability of an epsilon excursion, and if the probability of the epsilon excursion goes to 0, then you have convergence in probability. For convergence almost surely, you are not looking for a particular n, what you are doing is you fix a particular m and you are saying that beyond m there are no further excursions. Is that clear? Yes, with me? So, you see even in the 1 over n example we did, right, xn equal to 1 with probability 1 over n, see the probability of xn exceeding epsilon, namely xn being equal to 1 has very small probability 1 over n, but if you look at after m there will be some excursions, right, with probability 1. So, you do not have almost sure convergence, correct. Now, are you able to convince yourself that convergence almost surely implies convergence in probability? So, this theorem is this hammers everything, right, it proves that so that simple implication of almost sure convergence implying convergence probability is a trivial consequence of what we have proved, right. So, we have proven much more. You see why? Because our theorem, necessary and sufficient condition theorem, says beyond m there are no further epsilon excursions, which means at m there cannot be for any the probability of excursion is going to 0, you have therefore convergence in probability. So, that is fairly easy. So, corollary xn converges to x almost surely implies xn converges to x in probability. Okay. So, this is because see xn, so xn converges to x almost surely is equivalent to saying that limit m tending to infinity probability of bm epsilon equal to 0, right. But so bm epsilon is contained in am epsilon. You see why? See bm epsilon means m and beyond there is an excursion, or I think it is the other way, is it? So maybe I messed it up. Bm epsilon means there exists an excursion, right. So bm epsilon says there exists an excursion m and beyond, okay. Am epsilon means there exists an excursion at m, right. So, I wrote this is incorrect. So, I should really write that, correct, agreed. So, thus this implies limit m tending to infinity probability of am epsilon equals 0. Why? Bm is a bigger event, right, that has probability going to 0. So, you have convergence in probability. Of course, the converse we know is not true, right. We may have this probability going to 0, but you may have some excursion popping off for, right. So, we saw the situation where this probability goes to 0, but this probability does not go to 0, the 1 over n example we gave, right, but this direction easily follows. Okay, so, this result is a trivial consequence of the necessary and sufficient condition theorem we proved. Okay. So, I will stop here.